you guys, I'm recording my lesson, so if you're having a hard time reading everything, you can go ahead and listen to me do the problem as I kind of say what I'm doing. I'm not used to doing this, so if it sounds kind of weird, forgive me, first time and everything. But we're going to look at chapter 2.6 first, which is on building quadratic models from verbal descriptions. Make sure that you read the learning objective. The key part of this is to make sure that you know the revenue formula. So the revenue formula is R equals XP, where X is the number of units that you're selling, which is usually an unknown, and P is the price per item, usually as a function that's given to you. So let's go ahead and take a look at our examples for these. So problem number 1 says the price in dollars and the quantity X sold of a certain product obey the demand equation given. Part A, they want you to find a model that expresses the revenue as a function of X. And for part B, what quantity of X maximizes the revenue. So on problem A, we have P equals negative 1/4 X plus 300. So we're going to go ahead and find the revenue. That's part A. We're going to use the revenue function. And the revenue function is R equals X times P. So in our case, R will equal X, which is just X because it's unknown, times the price function, which is negative 1/4 X plus 300. Oops, 300. Let me put this 0 in. So we go ahead and distribute that. So we get R to be negative 1/4 X squared plus 300X. And that's it for part A. So for part B, they want you to figure out what quantity maximizes the revenue. So if you want to find the maximum of something, you're really looking for the vertex. And in this form, remember to find the vertex, we use the equation X equals negative B over 2A. So all we have to do is plug all these in. So X equals negative B, which is 300, divided by 2 and A is negative 1/4. So if we simplify this, we end up getting 600. So if we want to maximize the revenue, we need to sell 600 units. All right, let's go ahead and look at problem B. I'm going to go to the next page. So B says that X is equal to negative 20X plus 1,000, but I'm pretty sure that's not supposed to say X. I think that's a typo. It should say P. So they give you that as our price function. So the same idea. So for part A, you're finding the revenue. So revenue equals X times P, where X again is always just X. So R equals X. And P is the price function. And the price function is negative 20X plus 1,000. So we distribute to go ahead and finish what R is. So we get negative 20X squared plus 1,000X. So that finishes part A. So let's go to part B, which is to maximize the revenue. So same idea. X equals negative B over 2A. So in our case, X equals negative B, which is 1,000, over 2 times A, which is negative 20. So we simplify this one. We get 25. So in order to maximize the revenue, we need to sell 25 units. So those are our demand and revenue problems. So we're going to go ahead and look at the other problems, which are all done a little differently, but they all require some type of maximizing or minimizing. All right, so here on problem number 3, it says a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He does not need a fence along the river. What are the dimensions of the field of the largest area he can fence? So let's go ahead and picture this. Basically, there's a rectangular field. So here's my rectangle. I'm going to put fencing around every side of this rectangle, except for the side that has the river. So I'll put the river here. I'll make it in blue. So there's the river. So I'll need fencing everywhere. So in other words, he needs a fence here. I don't know how long that is. I'll call it X. And on the opposite side as well, same length, so it's X. But then I need a fence across the top. I don't know how big that is. That is Y. So they want us to find the dimensions that will maximize the area. So the area is length times width, or base times height. And in this case, it would be X times Y. Unfortunately, you can't maximize something with two different variables. So it's either has to just be x or has to just be y. So we're going to have to figure out what x and y is. And that's where this 2,400 feet of fencing comes from. The idea of 2,400 feet of fencing is basically saying that if I add all the sides that I need a fence on, which is x plus y, that should equal 2,400. So we simplify this a little. It says 2x plus y equals 2,400. So now we have the second equation that has both x and y in there. So we can go ahead and solve for y or x, either way. But I think solving for y is easier because all I have to do is subtract the 2x. So I'll get y equals 2,400 minus 2x. This is important because now that gives you an expression for y so that you can rewrite your x. So your area. So A is going to now equal x times y, which you now know is 2,400 minus 2x. So we'll go ahead and distribute. So that would be 2,400 times x minus 2x squared. So now that we have an area formula, we can go ahead now and maximize. So again, maximizing is still the vertex formula. So x is still negative b over 2a. And in our case, that would be negative b, which is 2,400, over 2 times a being a negative 2. So we simplify this a little bit, you get 600. So it's currently 600 feet. But you want the total dimensions, which isn't just the x value, you do need the y value. So we're going to go back to this equation here. We'll plug in the x to figure out what y is. So y is 2,400 minus 2 times x, which is 600. So if we simplify that, that's 1,200 feet. So our two dimensions are one side is 600 feet and the other side is 1,200 feet. All right, let's go ahead and move on to problem number 3.